already 9:30, so I will give a time and place to Professor Junichi Takahara. You can start your presentation now, please.
Thank you for introduction. Hello everyone. I am Junichi Takahara. I would like to start my lecture about metasurface. First, I would like to share Can you see my presentation?
Yes, Sensei, we can see the presentation.
Okay, fine. Okay. Okay, let's start. I'm working in Osaka University, Photonics Center, and I have been studying the plasmonics and metasurface and metamaterials and thermal radiations. And today's my talk. There's no response. Okay. First, many students are not familiar with metamaterial and metasurface, I guess. So I would introduce you the very basic aspects of metamaterials and metasurface. And then I will talk about our studies about plasmonic metasurface and perfect absorbers and its applications. And then I will talk about all direct metasurface, especially for silicon, very conventional material in industries. And if time is allowed, I would like to introduce the recent progress about the radiative cooling. But slide is too many, so I don't know. And finally, I will summarize. First, introduction. What is metasurface? Before say this, I would like to say about the material. As you know, material is simply composed of atoms, many atoms. Crystal or amorphous, anyway, material consists of many atoms. And like this, metamaterial is composed of a lot of meta-atoms. Meta-atom is artificial structures, human-made. As you can see, this is meta-atoms. This is atoms. And very simple. And in metamaterial, the size or period of the meta-atoms are much smaller than the wavelengths of the waves. In this, there are many kinds of metamaterials. Today, I focus to the electromagnetic metamaterials, optical metamaterials, photonic metamaterials. And in recently, acoustic metamaterials are emerging. But in this lecture, I'm focused to the photonic metamaterials. And for materials, atom is a natural resonator to electromagnetic waves. Like this, meta-atom is also the artificial resonator to electromagnetic waves. The definition is very simple. And metasurface is a two-dimensional metamaterial. The metamaterial was invented around 2000. This is very famous now, and this is because the metamaterial it was shows negative refraction This is a very strange property. As you can see here, this is a conventional refraction and this is a negative refraction. And this is not observed in natural materials. Very strange characteristics of the metamaterials. So the metamaterials becomes very famous for many peoples. And so first I would like to start how to realize negative refractions. What is negative refraction? It's very simple. In conventional refraction, as you know, the optical waves coming into this direction, theta 0, reflected this direction. Yeah, this is according to Snell's law, as you know. In negative refraction, the reflection angle is the opposite side, not this side, opposite directions. This is negative reflection. In this case, the index have a negative value. I mean, the refractive index is smaller than 0. This is negative refraction. Very simple. So the question is, how should we do to realize negative refraction? At first, please remember the definition of refractive index. Please remember. Refractive index is a ratio between the light speed in vacuum and in the materials. This is a simple definition. N equals C over V. V is light speed in materials. From the formula, you can change this formula to this one. We rewrite epsilon and mu. And then this is can rewrite to this and this, we can obtain this one. So refractive index simply the square root of permittivity and the square root of permeability, or relative permittivity, relative permeability. For non-magnetic materials, in conventional glass, for example, the relative permittivity is 1. So we can obtain this simple result, n equals square root of epsilon. This is a well-known formula. So if you have a glass substrate, refractive index is positive value and 1.4. We can have epsilon is 1.96. This is the square root of 1.4. This is very simple. So if we, but please remind, epsilon relative permittivity is positive value. So this is a positive value. And this is also a positive value, and this is also positive value, so always positive, not negative refractive index. So what should we do? And by using this formula, if we want to a negative value of n, we need to have a negative epsilon and a negative mu at the same time. Square root of -1 is imaginary number, I, and the square root of mu, if the mu is -1, this is imaginary number 1, and the I times I, the product of two imaginary number is -1. So in conventional formula, please, you remember this formula? This is not correct. This is the incorrect formula. This is -1, this is -1, this is +1. So the square root of 1 is 1. This is a positive value. So this formula is not correct. This is a correct formula. This was discovered in 2000, just 20 years ago. So the answer is very simple. If we get the negative refractive index, epsilon and mu have a negative value at the same time, at the same frequency. This sometimes called double negative. So we need to seek out the double negative material if we want to realize a negative refraction. Negative permeability and negative permeability is very natural. It is very well known. For example, the metal is known as a negative permittivity material below the plasma frequency. And also, negative permittivity is also well known. This is a magnetic material. But the problem is negative permittivity is achieved in the visible region, very high frequency, optical region, only in optical region. And the negative permittivity is only achieved in microwave or millimeter wave region. The very large frequency mismatch. In the optical frequency region, spin effect is very low in response, time response. So in the very high frequency, such as optical frequency, it's saturate, response is saturate. So the permittivity of the magnetic materials is almost 1 at the optical frequency. So we need to control the permittivity or permeability to the same frequency to become negative. So in this strategy, we can reduce the permittivity, negative permittivity to microwave frequency by artificial structures. This is a metamaterial. This can be achieved by metamaterials. So plasma frequency should be very small. So as you know, the plasma frequency is proportional to the square root of carrier density, square root of n. So we need to reduce carrier density of metal. So this is the answer. If we consider about the very thin metallic wire array shown here, the volume of the electron decreases to the bulk metal. This is a very thin wire. So the fraction of the free carrier is reduced in this region. So as a result, the effective carrier density much lower than the conventional metals. As a result, at the microwave frequency, the epsilon negative can be achieved in this thin metal wire array. And also, we can realize the negative mu at the same frequency range, microwave region, by using this split ring resonator. This is a very strange shape. You have a split here. This is a simple ring, metallic ring, 2 rings. And this is a gap, and this is also a gap. And if the magnetic flux is generated here, according to the electromagnetic wave flow, and there is a circular current generated here and here, the same directions. And this may induce the L And also, this is two coupled system of the two ring. So there is a capacitance here. This is inductance L. And capacitor and inductor make LC circuit. It's like a resonator. So we have a resonance at the microwave region. And as a result, we can obtain the negative mu. So if we put these meta atoms at the same space, within same space, this is a symmetric wire here, and this is a split ring resonator, and the electromagnetic wave is incident from this direction. So it means K vector is this direction, and this is an electric field vector, and this is a magnetic field vector H, and this is a TEM wave propagating in this K directions. And as a result, this thin wire is response to this electric field, and this split ring resonator responds to this magnetic field. So as a result, this symmetric wire shows a negative mu, as well as this is a negative, this is negative epsilon, and this split ring resonator shows negative mu. As a result, we have a negative index at the microwave region. This is the first demonstration of the negative reflux index material we call NIM, negative index material at microwave frequency. This was done by the David Smith group in 2000, 20 years ago. As you can see, there is a split ring resonator, copper split ring resonator here, and this is a symmetric wire here, and this is a print substrate, very large. This is a microwave, so the wavelength is centimeter order, so the size of the meta atoms is very large. So if you put into the electromagnetic field in this direction, this is the K vector. Electromagnetic is here parallel to the symmetric wire, and the magnetic field is through the split ring resonator. This artificial structures shows a negative refraction. This is the first experimental demonstration of negative index material at microwave. What happens in the negative refractions? This is a schematic view of the power flow, and the electromagnetic field is incident to this direction, K. And in this case, this is a conventional material, conventional direct material. This is a pointing vector direction. This means the power flow of electromagnetic field. And this is conventional. The direction of K vector and the pointing vector is the same direction. This is called right-handed material. This is a forward way. But in the negative index material, the situation is very strange. The power flow is the same direction. This means this is a pointing vector, but the direction of the K vector is opposite to the pointing vector. This is called the backward wave. The K vector and the pointing vector is the opposite directions. And as a result, the power is flowed in this direction, but the K is opposite. But the boundary condition is fulfilled properly because the projection of the K is the same in this interface. So anyway, this kind of strange bending is very strange, but this can be achieved. The physical property allows this kind of negative bending. The optical beam is bending just 90 degrees. This is a negative refractions. And okay, we can achieve the negative refraction. So what's applications? It's a very difficult question. But researchers are find the solution of the application of negative refraction, we can achieve the flat lens or super lens by using the negative refraction. What is super lens? Let's explain. And this is a conventional lens. This is a glass convex lens. This is a penguin image. The image is transferred to the light beam optical rays, this direction, and we can have an image, opposite direction image. But important things is this ray does not carry all the information of the penguin. I mean, the details of the penguin is lost during the propagation of the optical rays. This is because the fine structure of the penguin is carried by the evanescent waves. The fine structure of the penguin has a very high K wave vector, so it exponentially decreases its intensity and almost disappear in this image space. So as a result, the details of the penguin disappears in the image. This is called diffraction limit. So for this sense, conventional lens, for example, convex lens is an imperfect lens. I mean, all the information is not transferred to the image space. But by using the negative refractive material, for example, the n equal -1, this the situation is changed. And at first, anyway, negative refractive material achieve a flat lens. This is also useful. This is a penguin image, and this is a negative refraction bending, and this is also the negative refraction bending. And so we can achieve image at the same direction. This is opposite direction. This is the same direction. And we do not need a curved surface. This is very complicated, difficult to fabricate, but this is simple plane. So this is the driving force of at the early stage of research of metamaterial. Such kind of flat lens is we seek out and want to realize. And also in 2000, this was pointed out in very early days, 1968 by Professor Besrago. And in 2000, Pendry in the United Kingdom pointed out this kind of negative refractive index amplifies the evanescent waves and reproduce the perfect image, the imaging space like this. This is exponentially decay. The information is lost, but by using the negative refractive material, the evanescent waves can be amplified and generate this. This is a perfect transfer, the detailed information of the penguin to the image plane. This is a complete transfer. So this lens is called the perfect lens. This means non-diffraction limited lens. There's no diffraction limit in negative refractive material, but there is a problem. As I show you, by realizing the negative refractive material, we use metal atoms made of metals, say metal wire and split ring resonators. It consists of metal. It has a great loss. So during the propagation through the negative refractive material, the information is lost by the loss of metals. So the many interesting effects disappears through propagating the inside the metamaterials. So that's problems. So the researchers are planarize the bulk metamaterial and reduce the thickness of the material to reduce the loss of the metals. As a result, such kind of three-dimensional metamaterials consist of the several layers, only several layers, very thin. So the very thin metamaterial has a very low loss. So, but at this sense, this is several layers and still three-dimensional metamaterial. But if so, the researchers make a single layered metamaterials. I mean the two-dimensional metamaterial, only single layer, not the three-dimensional bulk. So the meta surface was born to protect the loss of the metals. Anyway, this is a meta material, two-dimensional metamaterial, so-called meta surface. The concept is very similar. The concept of meta surface is very similar to the metamaterials, but the physical property and the physical principle, operation principle is completely different between metamaterial and meta surface. In metamaterial, as I said, this is an effective index material, so-called effective medium. So we homogenize the fine structures, meta atoms and period, to the homogenize and obtain the single bulk, plain, homogeneous material. This is a metamaterial, three-dimensional bulk metamaterial. Because fine structures is very, very small smaller than the wavelengths of electromagnetic field. So electromagnetic wave does not feel such kind of detailed structures and period inside the metamaterials. But instead of this meta surface, this is not an effective medium because we have only one very thin layers. This is not the effective medium. By considering the meta surface, we consider the individual meta atoms itself and consider about the scattering from single meta atoms. That's completely different in physics. This is a very typical examples of the plasmonic meta surface, metallic meta surface. This was proposed from the Harvard Capassos group in 2011. And you can see a V-shaped optical metallic antenna is arranged here. And this kind of structure is very attractive for the propagation control of the interface. Here you can have an incident light beam, and this is anomalous refraction, but even the negative refractions. So this is a V antenna, and this is operation wavelength is 8 micron mid-infrared range. But anyway, this is a negative refractive index meta surface, not a meta material. So the only one single meta atom layer completely achieve the negative refraction. So we do not need a metamaterial, bulk metamaterial. We just only the single layer to achieve the negative refractions. This is a very dramatic change because in the early stage of research of metamaterial, we have a great effort to realize bulky metamaterials, but it's very difficult to construct the very small structures in visible or infrared regions, not the microwave regions. So many research has been achieved for control the optical waves by using plasmonic metasurface. For example, the generation of vector beam. This is a complicated arrangement of the metamaterials and V-shaped antenna, and this metasurface generates optical vortex like this. This is a very interesting applications. This is a simple example. This is a simple reflection angle control. This kind of linearly changed metal structure diffract the light in the reflected light. It's a different directions. Anyway, such kind of many proposals has been achieved in plasmonic metasurface, but we have still a great problem of huge loss of metals. So researchers are focused to the application of huge loss itself. This is a perfect absorb application. Or a second approach is to reduce the loss by using lossless materials. For example, the high refractive index material. This is a later one. First, I will talk about the perfect absorber applications. In plasmonic meta-atoms, theoretically, it is a plasmonic Mie resonator. For example, you can imagine the gold metallic nanoparticle here. The radius is 100 nanometer. This is an optical scattering cross-section of the fine nanoparticle here. As you can see, there is a resonance here, 600 nanometer visual range. This is called plasmonic resonance, surface plasmon resonance, for example. And this is a electromagnetic field simulation. Here you can see the electromagnetic field vector. This is a dipole resonance. This is an electric dipole. Plasmon is an electric dipole resonance. And there is a small part of the amount of the magnetic dipole resonance shown here, but it is very small. The dominant part is an electric dipole. This is a plasmonic resonance case, and this is called plasmonic antenna, optical antennas. And by using this kind of plasmonic nanostructures, we can realize a perfect absorber, as shown here. The structure is very simple, and this is called the MDM structure, the sandwiched structure, metal, direct metal. Yeah, very simple. This structure acts as a perfect absorber. The incident wave is all the incident wave is absorbed like a black hole to the particle itself. So the cross section is greater than the geometrical cross section of the nanoparticle. This is a very large enhancement of the absorption cross sections. And this is application of the perfect absorber. This is our studies. Here you can see the very beautiful color palette shown here. This is not a simulation. This is experimental results in the optical microscope. Here you can see very beautiful colors. This is not using the dye. This consists of the aluminum. Here you can see the structures. This is aluminum disc. Thickness is 40 nanometer, and a very thin oxide alumina. Thickness is 30 nanometer, and the substrate is aluminum. Thickness of 100 nanometer. So all the composition is alumina. And here you can see the same microscope. You can see a disk, nanodiscs shown here. But the diameter of disk is changed from 18 nanometer to 280 nanometer, gradually change. And this vertical line shows a period of change to the 200 nanometer to 400 nanometer. As you can see, if you change the period, the color is almost constant. This is period change, almost color is change. So in conventional structured colors, for example, by using photonic crystals, if you change the period, the color is drastically changed. Imagine the morpho butterfly. You can see a very beautiful blue colors in morpho butterfly. It was originated from the photonic crystal, and it depends on the periodicity of the structures, photonic crystals, multi-radial photonic crystals. So if you change the period of the fine structures, the colors will drastically change. But in metamaterial, this is not independent of period. Depend only on the diameter of the meta atoms. So it means each meta atoms active independently. So that's a difference between meta surface and the photonic crystals. As you know, aluminum has silver colors, and aluminum shows a transparent crystal. And if you have impurity in the alumina, you have very beautiful colors. But in the pure alumina, this is transparent, and alumina is silver. But we can achieve such kind of beautiful colors by using the meta surface, perfect absorber. Let me consider about the principles of the operations. Here you can see absorption map spectrum of these structures. This is a wavelength, and this is a diameter. This is a mapping. The color shows the absorption cross sections, and the bright color shows the high absorption cross sections. You can see two lines here and here, and these yellow region has great absorption cross sections. And at the diameter 160, we have two absorption peaks, A and B. And in this case, in A, we have a resonance, and here and inside the aluminum. And at the B, we have a higher mode inside the aluminum, inside the gap. So this is called the surface plasmon polariton resonance. This is if the electromagnetic energy inside shining this patch antenna, the electromagnetic field absorbed inside the gap region. This is dielectric, but gap is very, very small. So there is a cutoff effect. So the conventional optical wave does not penetrate into the gap region, but by using the surface plasmon polariton wave, there's no diffraction limit in surface plasmon polariton, and the electromagnetic field can penetrate into the gap and absorbs the light. So if you control the diameter, we can control the reflection colors because this is the absorption. So this is a Fabry-Pellot resonator. So if we control the diameter of the meta atoms, this is 80. The absorption occurs at 450 nanometer. So absorption occurs this one. So all the other wavelengths is reflected. So the longer wave length is reflected. So the color becomes red. And if we increase the size of the meta atoms to 120, and the absorption peaks red shifted for example, the 600 nanometer, so the color is blue. And more, 140, the absorption is 700 nanometer. So the blue one is reflected. So as you can see, such kind of, by changing the diameter of the metaatom, we can change the colors or reflected colors. This is an example. Here you can see a capital here, NO. And this is a 7 micrograph. This is very small. This is 100 nanometer, 120, 140. But if you look at this by optical microscope, you can see individual colors. This is a black, purple, and green, and blue. So this is the size of the pixel is only the 250 nanometer. So it means the resolution of this image is more than the 100,000 dpi. This is a huge, dpi means dot per inch. It's a huge resolution of the image beyond the almost the diffraction limit. This is results of the Dai Nippon Insats company, a Japanese very famous company of printing. They realize HK plasmonic color pictures, and this is the original pictures. And by using this technology, they realize such kind of very high optical printing in plasmonic colors. And here you can see the image. Image is very small, smaller than the pen tip. And the size is only 2 millimeter and 1.5 millimeter. But inside this one, you can see a very fine pictures. The color is something strange. But anyway, this is a very fine pictures. First demonstration of the 8K plasmonic color picture. But the color is a problem. The color space, this is the color space in the plasmonic color. The color space is not so wide. So this is a problem. So this is due to the loss of the metals. By reducing the loss, we need to replace the metal to the high refractive index materials, dielectric materials. This is all dielectric metasurface. So this is the second topic. We change the metallic structure, huge loss, to the lossless material. In dielectric material, we have another degree of freedom. This is a magnetic dipole. Here you can see two resonances. One is the electric dipole resonance. This is familiar in plasmonic resonance. And also, we have also a magnetic dipole resonance here. This is a magnetic dipole, and there's no monopole in universe. So magnetic dipole means a circular displacement current around inside the dielectric material. And this is an example of the silicon nanospheres. The radius is 100 nanometer. Here you can see a lot of peaks. This is completely different from plasmonic particles. And here you can see a very big peak here. This is not the electric dipole. This is a magnetic dipole. And this is electric. The second one is electric dipole. And the other is a quadrupole, magnetic quadrupole, and the electric quadrupole. And so many multipole can be generated in the all dielectric metasurface. This is a characteristic completely different from plasmonic metasurface. Here you can see time is almost up, so just the results of our silicon metasurface. This is a very simple structure, silicon cube. The thickness is only the 150. This is a single crystal silicon. The silicon is a typical material of high refractive index, the 3.88, very high. This is the results. Here you can see a silicon nanoblock, and we can achieve the color palette of the by using only the silicon. By using this one, we can control the magnetic dipole as well as electric dipole, both dipoles, and we can achieve the yellow colors by using two peaks, mean resonance. Okay, I skipped the results. So we can successfully expand the color space widely compared to the plasmonic. And we also add the chromium mask on top of the silicon meta surface, and we can achieve the very high confinement, and as a result, we can achieve a very fine, colorful, vivid colors. We can show purple colors by using the silicon and chromium mask meta surface. Here is a demonstration of the very beautiful color pictures of fireworks. And also we have a very high resolution, diffraction limited resolutions as well. Okay, I skipped the final region, and okay, thank you for your attention.
Thank you very much for the presentation, Sensei. So the time actually it's already up, but if we have one or two questions from participants, we can have a question. Okay, so this is question from Satria Sensei. Thank you for your presentation. As I know, plasmonic properties of metal surface can be used as a sensor. Can we use these plasmonic properties on metal surface as a sensor too?
Yes, yes, of course. In plasmonics, biosensor is already we have equipment, commercially available equipment. So we have a lot of application in sensor. Yeah.
Okay, I hope that answered the question from Satria. I also have one question, Sensei. What is the biggest application now in the industry of using metamaterials? Can you give an example?
Yeah, it's a difficult question. Unfortunately, we don't have a big application in metamaterial. Some sound is something wrong. Okay. Anyway, we don't have a big application in metamaterials. It's a problem of metamaterial community. One of the application is structured colors shown today.
Can we use for medical or medical applications, Sensei?
You mean biomedical? I cannot.
Yes, medical application.
Yeah, there are a lot of applications because if you have a metal surface here and put some biological molecule or biological material on top of the metal surface, the optical scattering properties drastically change. So it's very sensitive to the surrounding material. So it is simply applied to the sensor. Okay. But the important thing is there exists a lot of many kinds of sensors already. So the important thing is how better plasmonic materials or direct metal surface is better than the conventional sensors. That's the point.
Okay, Sensei, thank you very much. So I think there's no more question, but if the participants have further question, can they contact you directly, Sensei?
Yes, of course.
Okay, yeah. Maybe by email, right?
Yeah, email, please send the email. Yes.
Okay. So
Welcome.
thank you very much for the very interesting topics and very given new insight, especially for me. And I hope for all the participants.
Yeah,
And
yeah.
thank you very much, Sensei.
Yeah, thank
Hope to
you.
see
Bye
you.
bye.
Yeah,
Have a
bye.
nice
See you.
day.
Have a nice day.